So here's a quick review of trigonometry. Now I'm going to give you a crib sheet right here, which basically tells you all the ways to solve a right triangle. So you'll be dealing with these in trigonometry, and notice we have the Pythagorean theorem, and we also have the SOHCAHTOA equation, which tells you that sine is opposite over hypotenuse, cosine theta is adjacent over hypotenuse, and tangent theta is opposite over adjacent. Now another crib sheet I'm going to give you is this one right here, which tells you the basic trigonometric identities. So let's actually try some practice problems now. So we have this right triangle here, and a right triangle is any kind of triangle that has a 90-degree cusp like this. And we're trying to solve for a missing side x, and we're trying to calculate our angle in degrees. Well, to find this missing side x, I'm going to use the Pythagorean theorem. The Pythagorean theorem says that a squared plus b squared equals c squared, where c is your hypotenuse. So in this case, we'll have 3 squared plus 4 squared equals x squared. 3 squared is 9, and 4 squared is 16, so we should get that x squared is 9 plus 16. 9 plus 16 is 25, and then the square root of 25 is 5. So positive 5 should be the missing length of our triangle. Now let's see if we can calculate our angle theta right here. Well, I'm going to use the rules of SOHCAHTOA for this. Specifically, I'm just going to focus on the TOA, which tells us that tangent is opposite over adjacent. So tangent of our angle theta is opposite over adjacent. Now, the side opposite to our angle, if we go to our angle, the opposite side is 3. The adjacent side is 4. So we just need to plug in 3/4. If I take the inverse tangent of both sides, I'll get that theta is equal to inverse tangent of 3/4. If I type the inverse tangent of 3/4 into my calculator, make sure you're in degree mode, you should get that this evaluates to 36.9. So 36.9 degrees is the missing angle, and we have solved this right triangle. Now let's try verifying a trigonometric identity. So in this case, we have cosecants and secants, and we're trying to change everything to sines and cosines. Well, at least that's going to be our first step, because we're trying to prove that this statement is true. So to change everything to sines and cosines, I'm going to use this equation right here. This tells us that the sine of theta is 1 over cosecant. By the way, you don't always have to change everything to sines and cosines, but a lot of times it will just help visualize things a lot better. So what I'm going to do here is I'm going to take the cosecant and multiply it on both sides. That'll get the cosecants to cancel. Then I'm going to divide both sides by the sine of theta. That'll get the sine of theta to cancel, giving me that cosecant is 1 over sine theta. This also means that cosecant squared is 1 over sine squared theta. So I can take everywhere that I see cosecant squared theta and plug in 1 over sine squared theta. Now, using the same logic, since we see that cosine is 1 over secant theta, I can change the secant squared theta to 1 over cosine squared theta. Now, if I take this fraction and flip it and bring it to the top, I'll get that cosine squared theta over sine squared theta is equal to 1 over sine squared theta minus 1. I can multiply both sides by sine squared theta. That gets the sine squared thetas to cancel pretty much everywhere except for this negative 1 right here. So in this case, I'll have cosine squared theta equals 1 minus sine squared theta. I'll add the sine squared theta on both sides, and I'll get cosine squared theta plus sine squared theta equals 1, or sine squared theta plus cosine squared theta, I should say, equals 1. And in this case, we have a trigonometric identity that matches this. So if I take 1 and plug it in for sine squared theta plus cosine squared theta, I'll just get that 1 equals 1. And this is a true statement, so we have proven this trigonometric identity.